When we sample two random variables from the uniform 0-1 distribution in R, there's that which we see and that which is hidden. What we see are two colorless static numbers appear on our screen. But behind the scenes, a most colorful and dynamic algorithm is busy at work. In this video, we will no less than interview these two numbers about the journey they made in order to get to our screen. The story of that journey is the story of the Mersenne Twister algorithm, the default pseudo-random number generator, or PRNG, in most programming languages. This video is your invitation to see with your own eyes how this algorithm can create millions of pseudo-random variables. And it does so with ease, and it does so out of almost nothing. Since this is the first episode in a mini-series on Monte Carlo Methods, let's take a moment to contextualize it within the larger series. If we were to travel through time, witnessing the evolution of Monte Carlo methods, we'd make a first stop in 1777 when the accept-reject algorithm first appeared. Continuing our journey, we'd make two stops before 1950, at which point we make a major turn towards computation and away from further mathematization of the fields of probability and statistics. It shouldn't surprise anyone that this series on Monte Carlo methods will have the Metropolis algorithm, the Metropolis-Hastings algorithm, and the Gibbs algorithm as its core subject matter. These three algorithms will allow us to sample from any distribution out there, no matter how complex or multidimensional. But to do so, they rely on our ability to sample from any univariate distribution out there, and therefore they stand on the shoulders of two sampling methods that allow us to do just that: the rejection sampling and the inverse transform sampling methods. These two sampling methods in turn rely on PRNGs as they feed on random variables from the uniform 0-1 distribution. In this video, we'll have a look at two PRNGs, an ancient one, the middle square algorithm, and a modern one, the Mersenne Twister. Let's dive right in and start comparing the two PRNGs. On the left is a histogram of an increasingly longer sequence produced with the Mersenne Twister, using a seed value of 1958. On the right, an analogous one but produced by the middle square algorithm, using the same seed value. And notice that there is a two-part story to be told here. There's that which happens when the sample size is less than or equal to 41, and there's that which happens when the sample size increases beyond that. When sample size goes beyond 41, the histogram on the left settles into a uniform-looking one, which we'd expect it to. But the one on the right looks odd, as all the mass seems to be concentrated in just 4 buckets. To gain some more insight into what might have gone wrong with the middle square algorithm in this case, let's continue exploring the same two sequences under a different lens. This time, for each sequence, we'll do a dot plot of consecutive values. And this is what they look like when the sample size is 41. Once the sample size increases beyond 41, we see the left plot continues to update quite uniformly, but the right one seems to be frozen in time. In reality, both plots do update continuously with each frame, but what happens on the right is a little more subtle. If we look carefully, we'll notice that 4 of the dots in the right plot are somewhat brighter than the other ones. This is suggestive of overplotting. By now we have plotted 9,999 dots into each of the two plots, but in the right plot, the overwhelming majority of those dots went into the same 4 spots. It's time to have a look under the hood of the middle square algorithm to see what exactly went wrong in this case. The middle square algorithm starts by taking in the seed value that we provide, which is 1958 in this case. It then sets the input equal to that seed value. Next, it squares the input. In squaring an n-digit number, we get a number that has at most 2 n digits. Therefore, in squaring a 4-digit number, we get a number that has at most 8 digits. So, whenever input squared has fewer than 8 digits, the algorithm pads it with zeros at the front until it has exactly 8 digits. The output is then obtained as the middle 4 digits of input squared. The output then becomes the new input, and the process is repeated indefinitely. I colored the 42nd output in red, the number 9600, and recall that 42 was the sample size at which we were starting to see something strange in the middle square sequence of outputs. This 42nd output is a repeat of the output that was produced just 4 numbers before that. And from that point on, the algorithm enters into a cycle in which it outputs the same 4 numbers. You might recall that in the introduction, I called the middle square algorithm ancient. Primitive would have probably been a better word. And it is primitive because anytime the algorithm outputs a repeat value, it starts cycling from that point on. Modern PRNGs do not suffer from that flaw. Modern PRNGs can output a repeat value, and yet they will not cycle from that point on. We'll see exactly why that happens when we get to the Mersenne Twister. When we seeded the middle square algorithm with the value 1958, we have seen that it produced a sequence of length 41, at which point it broke down as it started cycling through the same 4 numbers. Therefore, we can synthesize our work into one single dot on this plot, which corresponds to 1958 on the x-axis and 41 on the y-axis. Of all the possible 4-digit seed values, there's one which produces the longest sequence. But with the length of the longest sequence at only 110, it is becoming clear that the 4-digit middle square algorithm will be insufficient for most practical purposes. Let's take a look at the 10-digit middle square algorithm and see if it does significantly better. As you probably guessed, there's a 2-part story here as well. and this time it hinges on the value 5792. When the sample size is less than or equal to 5792, the performance of the two algorithms is quite comparable and quite good. But once the sample size increases beyond that, we see that the performance of the middle square algorithm deteriorates very quickly, and all the math seems to be concentrated in just that first bucket. Continuing our exploration of these two sequences, we'll look at a dot plot of consecutive values. When the sample size is below 5792, we see that the performance of the two algorithms is comparable and quite good. When the sample size increases beyond that, we see that only the left plot updates. The one on the right seems frozen. Once again, there's one dot in the right plot that is brighter than the other ones. It's the one at the 0, 0 coordinate, indicating that most of the points went to that coordinate. Let's have a closer look to see where the middle square algorithm went off the rails this time around. It took in the seed value, set the input equal to the seed, squared the input, extracted the middle of the input squared as the output, and then repeated that process thousands of times. Until it broke down. And where exactly it broke down is not so clear. We could argue that it broke down the first time that it output a repeat value, which is the second time it output 0, the one in red. But an argument can be made that it broke down all the way up at that first value in yellow, the one that reads 46,801. The argument for it is that if the first half of an output is zeros, then the subsequent outputs will be decreasing to 0, which implies that from that point on, about half of the possible 10-digit numbers, the ones that don't have zeros in the first 5 positions, would have a probability of 0 of occurring. An argument can also be made that the algorithm broke down at that 0 value in yellow. The argument for it is that too many sequences end up in 0. Therefore, anytime we obtain a 0, we remove it from the sequence. But these are technicalities, and they won't address the flaws of the algorithm that we've been pointing out. It is possible to modify the middle square algorithm with a whale sequence, and that will dramatically improve its performance. We will not explore that here, because it is time that we turn the spotlight towards the protagonist in this episode. Let's start with a schematic depiction of the algorithm. The Mersenne Twister algorithm takes in the seed value, but unlike the middle square algorithm, it does not set the input equal to the seed. Instead, the initialize step of the algorithm uses the seed value to grow it to a very large number, and then uses relatives of that number to populate a grid of 624 cells. The twist operation then changes each of the 624 numbers so that we end up with a new grid of 624. The temper operation is applied to only one number at a time. If we requested only one number, then the temper operation would be applied only to the first number in our grid of 624. Notice, however, that the output does not directly feed back into the input, as was the case with the middle square algorithm. Instead, the interdependency in the sequence of output numbers comes primarily from the twist operation, which, every time it is called, transforms one grid of 624 into another grid of 624. Let's study this interdependency in slightly more detail. Notice from the definition of the twist function above that each number in the blue twisted empty grid is cooked up using 3 different numbers in the yellow empty grid. Take I equal to 0 as an example. Twisted empty of 0 refers to the first cell in the blue twisted empty grid. The number that goes into this cell is derived from 3 values in the yellow empty grid, these being empty of 0, empty of 1, and empty of 397. When I equals 1, twisted empty of 1 refers to the second cell in the blue twisted empty grid, and it is also derived from 3 values in the yellow empty grid. To see which 3 values those are, we have to evaluate 3 index expressions. The first one is just I, and with I being 1, it evaluates to 1. The second expression to evaluate is I plus 1 expression mod 624. When I is 1, it evaluates to 2. And the third expression to evaluate is I plus 397 expression mod 624. And when I is 1, it evaluates to 398. Therefore, the 3 values that it depends on are empty of 1, empty of 2, and empty of 398. We're almost ready for our first high-altitude step through the algorithm, but before we do that, let's do one last thing. Let's study the main operations of this algorithm: initialize, twist, and temper. In particular, let's examine the above directed graph to explore how often each of these 3 operations is executed as a function of the number of random variables that are sampled. Notice that the initialize operation is executed only once, no matter how many variables we are sampling, whether 1, 2, or 1,000. So, if we made an analogy to baking donuts, the initialize step is like turning the oven on. And we'll do that only once, whether we are baking 1, 2, or 1,000 donuts. The twist operation is only executed when the POS index is greater than 623. POS index refers to the current position in the grid of 624 numbers, while item identifies the variable that we are currently cooking. Notice that POS index is initialized with a value of 624 so that we take that upper branch right away and execute the twist operation, after which POS index is reset to 0. As we travel down, we see that in the next block, POS index will be incremented to 1. And the next time around, POS index will take the value 2, then 3, then 4, and so on until it takes the value 624. Once it takes on the value 624, we are back to that upper branch, and the twist operation will be executed a second time. Therefore, the twist operation is executed once for every 624 variables. The twist operation will twist each of the 624 numbers in the grid. So, even if we are sampling only 3 random variables, the twist operation will be executed once, which means that all 624 numbers in the grid will be twisted. Continuing our baking analogy, the twist operation is like the process of actually baking our donuts, and the Mersenne Twister will bake 624 donuts even if we asked only for 3. But the donuts are not ready until they have been tempered. So let's have a look at the temper operation next. The temper operation is executed as many times as there are random variables. So if we are sampling 2 random variables, temper will be executed 2 times. And if we are sampling 1,000 random variables, then it'll be executed 1,000 times. In our baking analogy, the temper operation is like adding all the frosting and sprinkles to the donut after it is baked. And importantly, we will do so only for the 3 donuts that have been requested, even though we baked 624 of them. It's finally time for our high altitude step through the algorithm. And keep in mind that the idea here is to see the big picture. We'll go into every detail when we do our low altitude walkthrough. The first thing of note that happens is that the initialize step is executed. The initialize step consists of 2 sub-steps: grow input seed and sow seeds. Grow input seed will take the seed value that we provide and will grow it to a very large number. Then sow seeds will use relatives of that very large number to populate a grid of 624. Once the initialize step is complete, we're on our way. With item having a value of 1, the first condition is met, and POS index having a value of 624, the condition is met, and we are ready to execute the twist operation. As you know by now, the twist operation will twist each of the 624 numbers, so we end up with another grid of 624. POS index is then reset to 0, and we're on our way. We're ready to temper the first number. We will temper the number with an index position of 0, which is the first number in the grid. Once we're done, we're ready to return the first integer output. We then convert the integer output to an output in the unit interval, and we're ready to increment the POS index and increment item, and we're back on the road. With item equaling 2, the condition is met. POS index equaling 1, the condition is not met, so we take the lower branch, and we're ready to temper another number. This time we'll temper the number with an index of 1, which is the second number in the grid. When we're done, we return the integer output and a corresponding output in the unit interval. We then increment POS index and increment item. And we're back on the road. With item having the value 3, the condition is not met, and we exit the algorithm. It's time for our low altitude walkthrough, in which we will open every black box and look at every detail. When the algorithm is executed, the first thing that happens is that the initialize step is triggered. And I should address 2 important points here before we move on. If you use the Mersenne Twister implemented in R and compared it to its implementation in a different language, such as Python for example, you'll notice that you will get 2 different sequences of numbers even if you seeded them with the exact same value. There are 2 main reasons why implementations of this algorithm may differ. The first reason has to do with how it is seeded. In other words, this initialize step that we're about to explore. And the second reason has to do with whether it is 32-bit or 64-bit. The seeding that I will describe here is Ripley's seeding, and it is precisely the method implemented in R. We'll look at a 32-bit implementation of it, same as ours. That means that the largest possible integer value that we can produce with this algorithm is the number whose binary form consists of 32 ones. This number being the largest number that we can produce, and 0 being the smallest, we see that there are a total of 2 to the power of 32 numbers that we can produce. Therefore, in order to convert from a 32-bit number to a number in the unit interval, all we need to do is to divide the number by 2 to the power of 32. That is how we convert from an integer output to an output in the unit interval. The initialize step consists of 2 sub-steps: grow input seed and sow seeds. Grow input seed will take the seed value we provided and we'll use this loop to grow it to a very large number. When this loop is done, we will have grown our seed value to the very large number at the bottom of the screen, which for simplicity we will refer to as G0. The grow input step is now complete. What it accomplished was to grow the seed value we provided, 1958, into a very large number that we called G0. We then move on to the sow seeds step. In this step, we go through another loop, which will first further grow our large number. It will use the value of G0 to calculate G1. Here's what G1 looks like in both base 10 and base 2. What the second step in the loop does is to take this number in binary form and keep only its last 32 digits and discard the rest. The 32-digit number we kept is then translated into base 10. Then we do the same thing, calculating G2 this time around. And here's what G2 looks like in both base 10 and base 2. And once again, we'll take this number in binary form, keep only its last 32 digits, and discard the rest. And then translate it into base 10. So far, you have seen in detail what happens when I takes on the values 0 and 1. But as you can imagine from the loop above, we will have to go through this process a total of 624 times, letting I take on values up to 623. And as you might have guessed, the numbers we have obtained are the numbers that will go into the grid of 624 numbers. As soon as all 624 numbers make their way into the grid, the sow seed step is complete. This in turn implies that the initialize step is complete and we're ready to move on. With item having a value of 1, the first condition is met, and with POS index having a value of 624, the second condition is also met, and we take the upper branch and execute the twist step. Now here are the algorithm constants. There's a different set of constants for a 64-bit implementation, but as we mentioned, we're looking at a 32-bit one. As you already know, the twist step will twist each of the 624 numbers in the grid, and it will do so by running through the loop above, letting I take on values from 0 to 623. And notice that at the end of each iteration of the loop, twisted empty of I is born. These twisted empty of I values are the values that will go into the new grid, the output of the twist operation. And don't worry if that twist set of operations above is a bit intimidating. That's what this video is here for, as in the next segment we will bring it to life. Well, this is the heart of the algorithm. It's the meat and potatoes. So I will just keep quiet for a bit and let you enjoy it. And we have finally finished twisting the first number. That's quite an achievement. We then go through this whole process one more time when I equals 1, and we will do it again and again, a total of 624 times. And what we will have accomplished at that point is to take the initial grid of 624, that was the output of the initialize step, and twist each of the 624 numbers to obtain a new twisted grid. This is the output of the twist step. With the twist step now complete, we are back on the road. The first thing we do is we reset POS index to 0. And then we travel down. As we enter this new block, we see that the first thing that we will do is to temper. To be precise, we will temper the number sitting in the twisted empty grid in position with the index POS index, which is 0 in this case. Therefore, we will temper the number sitting in position 0, and that refers to the first cell in the twisted empty grid. I'll admit that this temper step looks a bit intimidating. There are quite a few operations in there. But once again, I will bring it to life for you, and I hope that in the process you will find it less intimidating. And believe it or not, we are done tempering that first number. And the number we obtained is 280-234-0540. For ease of reference, I'll refer to it as the number that ends in 540. I will just briefly remind ourselves that the number that we just tempered is the first number in the twisted empty grid. That number was the input into the temper operation. Having completed the temper step, we are ready to return the first integer output. And of course, that first integer output is that number that ends in 540. Then we return a corresponding output in the unit interval, increment POS index, and increment item. And we're back on the road. Item being 2, the condition is met. POS index being 1, the condition is not met. So we take that lower branch, and we are ready to temper the number sitting in the twisted empty grid in the position with index POS index, which is 1 in this case, and that refers to the second cell in the grid. And we are done tempering the second number. Therefore, we are ready to return the second integer output and a corresponding output in the unit interval. We then increment POS index by 1, increment item by 1, and are back on the road. With item equaling 3, the condition item less than or equal to 2 is not met, and we exit the algorithm. When we sample two random variables from the uniform 0-1 distribution in R, two colorless numbers appear on our screen.